Welcome, ladies and gentlemen, to an intellectual odyssey. An odyssey that I hope will be as fantastic to you and as exciting as Homer's Odyssey without keeping you away from home for 20 years. Our odyssey will be a survey of the evolution of the sciences and of the relationship between science and society in the course of the 20th century. An intellectual history, then, of the physical life and social sciences. And I specifically emphasize that we will be spanning the ideas and theories characteristic of the physical life and social sciences in the 20th century without distinguishing between the so-called hard sciences of physics and chemistry and the so-called soft sciences of economics and sociology, because it is through their intellectual unity, through the common ideas and theories, that we get a sense of science as a cultural phenomenon in the 20th century, and because, from the point of view of society, science is a unity. Rightly or wrongly, the science-society relationship is driven by a perception of the unity and the intellectual integrity of the sciences. So we will be looking at both the intellectual inside of science and the social context outside of science, and seeing these as two sides, so to speak, of the same coin, distinguishable but not separable. And this has been, for me, the primary professional and intellectual commitment of my career. For almost 40 years now, I have been studying and teaching the history and philosophy of science from the perspective of the social context within which the conceptual framework of the sciences develops. I specifically use the term evolution, which I am borrowing from biology. In the minds of Charles Darwin and Alfred Russel Wallace, evolution meant the emergence of novelty by introducing discontinuities into an underlying continuity. This is a critically new and highly innovative concept in the 19th century that becomes very much more important still and of broader application in the 20th century. Evolution means that in time, unpredictable novelty emerges. And the way that it emerges is because an underlying continuity is transformed by unpredicted discontinuities. In the case of biology, we call them mutations, for example, that for biology gives rise to new species. But in intellectual history, there is an intellectual analog of mutations, ideas that transform earlier ideas without dispensing with them. And this is why I believe it is valuable to look at science in the 20th century as an evolutionary outgrowth of 19th century science and not a revolutionary rejection or displacement of 19th century science. Because that would suppose that because 19th century scientific theories are now considered to be wrong, so they are irrelevant. They're gone. They're history. On the contrary, they are living elements within the transformed theories of 20th century physical science, life science, and social science. Our odyssey, our intellectual history, will be organized not by discipline, but around five broad themes. The theme of matter and energy, the theme of the universe and our conception of the universe, of what we mean by the term universe, contrasting 1900 and 2000. The earth, our understanding of the earth, life, and mankind. Those will be the five themes, and we will also be looking at several seminal developments in mathematics that were profoundly influential on the practice of science and on the ways that science was applied in the course of the 20th century. I want to emphasize that because ordinarily abstract mathematics is simply dropped out of presentations of the history of science. And yet some of the most exciting intellectual developments in the 20th century came from a small number of developments in mathematics. And we'll be looking briefly and, of course, qualitatively at those. Our survey of the sciences will then have this dual character. It will have the intellectual inside interwoven with, but occasionally we will look specifically at the social context outside. If, as I said, we are going to do a survey of the evolution of 20th century science out of 19th century science, then we need to identify the core ideas of 19th century science that provided the continuity that was transformed into new kinds of ideas and theories in the 20th century. And I want to highlight 8 of these. This will get us started on the theme of matter and energy, but we will find that these ideas recur in different forms across the sciences. And as need be, we will introduce new 19th century ideas as we talk about some of these other themes as they're appropriate. But for right now, there are 8 ideas that I'd like to call your attention to. One is the idea of the atom. Normally, we think of the atom only in physical terms, but let's understand what in the 19th century the atom came to represent. It came to represent the view that natural phenomena consisted of fundamental building blocks that could be configured to produce the multifarious phenomena of nature. So, of course, the physical atom is an instance of that. And, of course, the chemical atom is an instance of that. But the gene is also an atom. That is to say, it is an atomic view of inheritance. A theory of inheritance based on the gene, which was Gregor Mendel's contribution in 1865, recovered in the 1890s, and 20th century genetic theory is based on that. That, too, is an instance of the atom. The germ theory of disease is an instance of the atom. And so when we think of the atom, it is a way of looking at nature not specifically tied to material atoms. It's not a question of oxygen and nitrogen and iron. It's a question of looking at natural phenomena as if they were composed of fundamental elements like Lego blocks that were linked together. The second idea is the idea of energy. The idea of energy in the 19th century is a fundamentally new idea. Of course, people had names for what we would call, let's say, mechanical energy today, but in the 19th century, a science of energy was created in the middle of the 19th century. It got the name thermodynamics, that recognized that energy was a phenomenon in nature parallel to matter. Until the rise of the concept of energy in the mid-19th century, modern science was committed to the view that all natural phenomena could be explained in terms of matter in motion. It is what, in other terms, is called materialistic determinism. The idea that all natural phenomena are the result of matter in motion. Matter, in the 19th century, has an atomic constitution. Given the properties of atoms, and given the rules for configuring atoms, you can put matter together. And then when matter moves, it generates all the phenomena of nature. That is the core dogma of modern science until the 19th century, when the concept of energy is introduced. Energy becomes a new dimension of reality. And the science of thermodynamics was the name given to this generic theory of energy. Energy does not exist in the abstract. It always takes a concrete form. There's heat energy, gravitational energy, mechanical energy, electrical energy, chemical energy. But the theory of thermodynamics is a general theory of energy which correlates all of these different kinds of energy. So the concept of energy is one of the most innovative ideas of 19th century science, and it is one of the elements of 20th century science that's not gone away, but it was fundamentally transformed, as we will see. Third, the idea of the field. And here we begin to see how ideas generate offspring of their own and sometimes unexpected interactions. The word field in 19th century science referred to something that should not have been part of a science based on materialistic determinism. A field is an immaterial something which is capable of exercising forces on material objects, almost ghostly. So, for example, an electrical field has no mass. It extends throughout all of space, but if you take an electrically charged particle and bring it into that field, it will experience a force, either of repulsion or attraction, depending on what the source of the field is. If the electric field surrounds an electron, which has a negative electrical charge, The electron was not known in the 19th century. Then if I bring another electron into that field, it will experience a repulsive force. But if I bring in a proton, another 20th century particle, it will experience an attractive force. But how did that happen? There's no physical contact between the electron and the proton. It was the field that did it. So this notion that energy, that there can be physical realities that are not material realities, and that these immaterial realities can be described accurately, that they observe laws, and that they can exert forces also on material objects, is a profound intellectual development in the 19th century that becomes crucial to understanding 20th century science. 4, the 19th century discovery by chemists that structure matters. It's a subtle point, but until it was realized that structure matters, the prejudice of science was that what mattered were the fundamental constituents of reality and their properties. What chemists discovered in the 1830s and 40s and 50s was that the physical arrangement of atoms in three-dimensional space changed the properties of the molecules that resulted. Knowing what the atoms were that made up a specific molecule and knowing all the properties of those atoms would not allow you to predict the property of the molecule unless you knew how those atoms were configured in three-dimensional space. And this was a very surprising discovery. Structure mattered. This concept that structure matters in the 20th century will become transformed into the idea that relationships are real, that relationships, like fields, can have properties and can exert forces. Because until you recognize that, you think that only things can be real. And that is a prejudice in the West that goes all the way back to Aristotle. And it was a very deep-seated prejudice that began to be undermined in the 19th century, but really was transformed in the 20th century. So we've got four things so far, 4 what I've called core ideas: the idea of the atom, the idea of energy, the idea of the field, and the idea of structure. We're going to have 4 more. Fasten your seatbelts for this one. Non-Euclidean geometry. Now, not many people study non-Euclidean geometry in their spare time, fascinating though it is for those who love it. But non-Euclidean geometry was discovered in the 19th century, and it sent intellectual shockwaves through Western culture that would be very difficult to overestimate. For approximately 2,300 years, prior to the mid-19th century, Western science, Western philosophy, Western mathematics was based on the confident assumption that deductive reasoning was closely linked to truth. That if some set of ideas could be organized deductively, then that was a sign that those ideas were true. So, for example, in the case of what we call Euclidean geometry, which is a set of theorems describing the properties of mathematical objects like triangles and circles and spheres, etc., based on axioms, definitions, and postulates, which are considered to be self-evidently true. The Greeks and almost nobody challenged this for 2,300 years, that these definitions don't need any proof. They're just obvious as soon as you understand the words. The assumption was that because the theorems of Euclidean geometry were deduced in strict logical fashion from these self-evidently true axioms, definitions, and postulates, that therefore Euclidean geometry was true about space, that it was the geometry of the space in which we live and move. In the middle of the 19th century, independently, 3 mathematicians, and possibly 4, discovered that you can have deductively perfect geometries that contradict Euclidean geometry. And now the question becomes, which of these geometries is true of real space? But now that becomes an empirical question. It can't be answered deductively. you have to do it experimentally. But once it's experimental, then it loses its logical purity and beauty. The discovery of non-Euclidean geometries in one blow severed the mindless, uncritical connection between reasoning and reality. We could never again be as confident as Descartes and Spinoza and Leibniz were in the 17th century, as Kant was in the 18th century, that if a theory were worked out deductively, then it must have some truth to it. All of a sudden, the connection between reason and truth, reason and reality, was made problematic. I want to mention two other developments in mathematics, which we will take up in some more detail in the lectures on mathematics, but I won't go into them in much detail now. And one is the invention in the 19th century of symbolic logics. And this is connected to the concept of relationships being real, the concept of the field and of structure, the two ideas that we just talked about, because symbolic logic teaches us several powerful lessons without understanding any symbolic logic. Just as you didn't really need to understand non-Euclidean geometry to appreciate how the invention of non-Euclidean geometry, or the discovery, depending on your view of these matters, of non-Euclidean geometry, could have a tremendous intellectual impact. Symbolic logic teaches us, let's say, two lessons. One, it reminds us that notation can have a tremendous intellectual impact. Simply replacing words with symbols can lead to new kinds of insights. You know, in the 16th century, equations in mathematics were words. They were written out in sentences. What we recognize as mathematics, the plus sign, the minus sign, the equal sign, those were all invented in the 16th century. And they transformed mathematics. All of a sudden, mathematics exploded. And it's probably related, in part at least, to the existence of a symbol system. Into the 19th century, the prevailing form of logic, which was laid down by Aristotle, just as the prevailing form of geometry was laid down by Euclid in the 4th century BCE Greece, the prevailing view of logic was that subjects had priority over predicates, that things were the ultimate reality, and relationships were a secondary consequence of the way things were organized. But symbolizing logical relationships suddenly called attention to relationships and the discovery that relationships had properties of their own, independently of what they related. For example, the parent-child relationship has properties that the sibling relationship doesn't have, and you don't have to know who the siblings are. You don't have to know who the parent and the child is to know that, the parent-child relationship is not symmetric. If A is the parent of B, B cannot be the parent of A. But the sibling relationship is symmetrical, as the brother-sister relationship would not be. If A is the sibling of B, then B is the sibling of A. So there's an example, a simple example of a relationship that has properties of its own. And the recognition of this led to a hierarchy of abstract logics which built on the properties of the relationships and relationships between relationships, etc. And this strengthened, in the 20th century, this strengthened the conviction that relationships had a reality and did not have to be reduced to configurations of things. The sixth of the 8 ideas that I want to call attention to in the 19th century that are critical for understanding 20th century science, and not just physics, the wave theory of light. From Newton in the end of the 17th century until the end of the first third of the 19th century, the prevailing theory of light was that light was like tiny little ghostly atoms, which Newton called corpuscles. Newton formulated a corpuscular theory of light, which in the 19th century was finally discovered to be utterly inadequate, and it was replaced by the theory that light was made of waves, was a wave phenomenon. Because it's a wave phenomenon, waves are distributed in space. Waves have a certain periodicity, a frequency they're called. They have a wavelength. Each wave has a characteristic length, etc. And so the wave theory of light, it became one of the great triumphs of 19th century science. It was perceived in the 19th century to be one of the great triumphs of 19th century scientists to have improved on Newton's corpuscular or atomic theory of light, in which light was like a stream of little bullets. Coordinate with the wave theory of light and really its maturation. In 1865, James Clerk Maxwell, Scottish physicist, published an electromagnetic theory of energy, of which light is just one type. Light is just one set of frequencies within the total spectrum or spread of frequencies of electromagnetic energy. A little below light, a little below the visible level is the infrared level that we experience as heat, and a little above it is the ultraviolet level. But when you go, which causes sunburn, among other things, but when you go way beyond it, then you're out into X-ray land, for example. And so Maxwell's electromagnetic theory of energy, which, by the way, explained what it meant to say that light was a wave, was perhaps the most important theory in physics by the close of the 19th century. Idea number 7, probability and statistics. That there were natural processes that required probabilities in order to describe them. In the 20th century, this becomes a principle of nature in quantum theory, but in the 19th century, in order to explain the relationships among the pressure, volume, and temperature of gases, Maxwell and an Austrian physicist named Ludwig Boltzmann had to introduce the idea that probabilities, statistics, were not just a function of our ignorance of the information we needed to give a total picture of nature, but that, in fact, certain fundamental natural phenomena were by nature probabilistic. And this was merely suggested in this kinetic theory of gases of Maxwell and Boltzmann, but in the 20th century, this becomes a very important concept. And finally, of course, the idea of evolution, which we've already discussed. Now, I'm going to mention 3 of the many discoveries and of the many instruments that were invented in the 19th century. 3 need to be called attention to because they are going to recur throughout the course. First of all, the color-corrected microscope. The microscope had become useless by the beginning of the 19th century because the things people were interested in looking at required powers of magnification that were beyond uncorrected microscopes. The corrected microscope, which allowed you to have high power magnification without blurring, was introduced in the 1830s and 1840s, and by the end of the century, biologists could see not only cells, but the nucleus within the cell, and within the nucleus structures called chromosomes, that were called chromosomes. So the color-corrected microscope was a very important discovery, and so were 2 other instruments that are less familiar to us. One is called the spectrometer. Actually an extraordinarily simple device, not that easy to make, but conceptually extremely simple, which when you pass a beam of light through the spectroscope, it breaks up the light into the various frequencies of which it's composed. And this will turn out to be a critical instrument for building up a body of data that quantum theory for the first time explained. And the second instrument, even more unfamiliar than the spectroscope, is the interferometer, invented by Albert Michelson, who was the first American to win a Nobel Prize. He won the Nobel Prize for Physics at the turn of the 20th century. And Michelson invented a machine. His fascination in life was getting the speed of light down with excruciating precision. And in order to do that, he invented a machine that allowed, essentially, allowing 2 beams of light to overlap. And then by doing this, the interferometer allows you to measure extremely small distances. Interferometers are in use in industry and research labs all over the world today. But that device will turn out to be of critical importance to us when we move on to talk about quantum theory. I've talked about the intellectual inside of 19th century science. How about the social context outside? What there became critical to understanding 20th century science and from the outside in terms of the social context? Well, there are 2 areas that I want to call your attention to. One is the emergence in the 19th century of technological innovation as the primary agent of social change, as it has been for the last 200 years now, as it is today. Technological innovation replacing religion and politics as the primary agent of social change. Technological innovation in the 19th century increasingly became entangled with science, so that in the 20th century, people talk about technoscience, science-based technological innovation. In the course of the 19th century, the transformation of communications industry, transportation industry, power generation industries increasingly became dependent on a scientific foundation. And in chemistry, this was particularly obvious, for example, as chemists began to create wealth and power through the synthetic dye industry, the pharmaceutical industry, and the synthetic materials industries, with military applications in the area of powerful explosives and propellants for artillery shells, for example, so that by the end of the 19th century, science and technology had become entangled, and three developments reinforced this. First of all, the invention of the Industrial Research Laboratory. Secondly, the emergence of the university as a center for scientific research. We take it for granted today, but until the 19th century, universities were transmitters of traditional knowledge. Professors were not expected to generate new knowledge. That was an outgrowth of science and technology-based research in Germany especially, and then that model was copied here in the United States. And finally, the government involvement in science. Governments deliberately leveraging scientific research in pursuit of military, economic, and social policies. So that is a quick and dirty look at some of the most critical 19th century elements which will have changes rung on them in the 20th century. They will become the materials that get transformed into, by way of new ideas, into new kinds of theories and new interpretations of those same ideas, new interpretations of Adam, etc. Let's jump ahead and let me identify for you 6 ideas that cut across the disciplines in 20th century science. 6 ideas that we will find in the physical sciences, the life sciences, and the social sciences. And one of these I have already mentioned, and that is the idea that relationships are real. Not only real, but increasingly perceived to be the ultimate reality, which is in some sense counterintuitive. Well, but what are the relationships among? Well, that turns out to be irrelevant. We'll see when we talk about contemporary quantum theory at the end of the 20th century that the idea that reality is ultimately describable in terms of relationships and the relata drop out is an incredible inversion of 2,500 years of Western intellectual history, when we attributed reality to things. And now, by the end of the 20th century, relationships become what science has to pin down, not things. Correlated with that is the concept of system. Looking at natural phenomena as systems. Big difference between Lego block building up from the bottom and looking at things as wholes in which every part has to be understood in terms of its relationship to the whole. So systems thinking is top-down thinking. So that's one set of ideas, relationships and systems. The second, dynamism, accepting change as normal and not trying to reduce it to stasis. By the same token, in the 19th century, scientists looked for equilibrium situations. How does a natural situation come back to equilibrium, as is peace and harmony with the norm in nature? In the 20th century, scientific theories increasingly look at non-equilibrium situations from which we have discovered that nature is capable of self-organization. And that will become critical when we try to understand life. Third, information as a feature of reality. Not as a fact, not as a statement about what we know, that information, like matter and energy, can be a category of reality. Fourth, the emergence of complexity out of simplicity. It was an intellectual discovery in the 19th century that you could get unlimited complexity from the combination of simple things. You don't have to have a complex foundation in order to have a complex superstructure. 5, quite extraordinary, the recognition in the course of the century that the distinction between subjectivity and objectivity, between mind and world, is not so clear-cut. And this will come up again and again in physics, no less than in the social sciences. And finally, in the course of the 20th century, scientific research became increasingly cross-disciplinary and collaborative. Not the individual researcher hero that we see in 1900, and not a focus on, I'm a physicist, I'm a chemist, I'm a biologist, but cross-disciplinary research and collaborative research. That is the basic structure of the Odyssey that we will be embarking upon. And in the next lecture, we will begin by undertaking the special and general theories of relativity. Thank you.